Hi class, I wanted to show you an example of a type of problem where you could actually evaluate a function at a certain x value, but without plugging it in directly, but rather using synthetic division and the remainder theorem. Remember that if I were to be looking for the zeros of a function, for example, I would typically test a number, let's call that number a, and that would be testing whether or not x minus a is a factor. And if I got 0 as the remainder, then that meant that when you plug in that number a into the function, you get 0 as the output, as the remainder. So for the same idea here, if we wanted to plug in a number like 0.1 into the function, another way of evaluating the function would be to do synthetic division with 0.1 as the a in that case. So for example, in order to do this, I could put 0.1 in my little synthetic division box, and I could remember how to do synthetic division. I would use the coefficients in descending order. So coefficient of x to the fourth is 1. The coefficient of x cubed is 0.4. The coefficient of x squared is negative 0.3. Notice carefully here that the coefficient of x is missing, so we need to put a 0 as a placeholder, and then the constant is negative 21. And then we could apply our synthetic division skills here, and we remember that we bring down our first number here, 1. We multiply, the algorithm says multiply by that number by whatever's in the box. 0.1 times 1 is just 0.1. The algorithm continued, if you remember, by adding these numbers together, the same sign, so that's pretty easy. 0.5 is our result. We repeat the algorithm in the next iteration by multiplying 0.1 times 0.5, giving us positive 0.05 or positive 0.05. We could combine that by addition again. Notice here that negative 0.3 is the same as negative 0.30. So when I combine that with a positive 0.05, what do I get? I get negative 0.25. And again, I can multiply that by what's in the box. 0.1 times negative 0.25 gives me negative 0.025. Again, proper technique is to put the 0 in front. I just ran out of space here, negative 0.025. But when you combine that with 0, because that was the missing term for the x term here, the missing coefficient for the x term, we get negative 0.25. Multiplying that by whatever's in the box, that's going to give us negative 0.0025. Again, proper form would be a 0 in front of the decimal always. And then adding that together with the 21 that's also negative produces our remainder of negative 21.0025. So what we found here is that if I put in 0.1 as the x input, the output is this remainder here from synthetic division, negative 21.0025. That's what we're getting here. And you can verify that just simply by doing your order of operations carefully and plugging it back in. But go ahead and try on your own 0.5. You set it up the same way. If you're evaluating for that a, you put 0.5 in your box, and you'd set up your synthetic division again with your coefficients, 1, 0.4, negative 0.3, 0 for your placeholder of the x term, and negative 21. And when you go through that process, you should end up getting, again, bringing down, multiplying, adding, etc., you should end up doing all of that stuff and end up with a result of negative 20.9625. Which means that's the result of evaluating the function at that input. At the input 0.5, the output should be negative 20.9625. See if that's what you got. Okay? If not, it could just be the arithmetic, so watch yourself carefully. Feel free to use technology if needed. But again, this is an alternate way of evaluating a function using synthetic division and the remainder theorem. So you didn't even have to necessarily plug it in directly, but rather indirectly, seeing what the remainder would have been. That's telling us what the result of plugging in that number as your a into the function for x. I hope this was helpful. If you have any questions, please feel free to reach out to me. Otherwise, happy practicing, because math is not a spectator sport. I'll see you next time.